Okay, so number one, you are in Georgetown, Texas, which is 30 miles from Austin. You're traveling north 30 on I-35 towards Dallas, going to 70 miles per hour. So we're going to fill in this table. And as you can see from here, we're going, we're starting 30 miles from Austin, and then we're going 70 miles per hour. So after 1 hour, I've gone an additional 70 miles, and then I go another 70 miles per hour. So I'm basically going to start off with, oops, let me get my pen. We're going to start off with 30, and then I added the two previous 70s, and then I'm going to add another 70. So we're basically doing 30 plus 70 times 3, which is going to get me to 240. So that's 240. And then the next one, I'm doing the 3 previous ones, the 30 plus the 3 previous 70s, plus I'm adding a new 70. So now I'm doing my original 30, plus now I have 4 70s. That's going to get me going 310 miles in that 4 hours. So if I don't do the math and if I follow the pattern, I'm doing 30 miles originally, plus 70 times 10. That's going to give me 70 times 10 is 700, plus 30 is going to take me to 730. So I've gone 730 miles in 10 hours. So my equation, my number of, miles driven, going to be equal to 30, which is where I started initially, plus 70 times my number of hours. Okay, so I don't know why that's so big. That doesn't need to be that big. Okay, so on the graph, they want to know the input and the output. So your input basically is your time in hours, because that basically is where you're starting with. As time goes by, it's your number of miles that changes. And your relationship is linear. Yes. It says interpret your rate of change. And basically your distance, the distance increases 70 miles each hour. So when I ask you to interpret the rate of change, you have to tell me basically your distance, your output, what your rate of change is, and then what your input is. And then which input value gives you an output that is equal to your initial distance from Austin. And that basically is 0. So that was when you were at time 0. You were at your 30 miles. So that was basically your starting point. It says it's very important for the input of 0 to produce your initial value. That's essentially what you need to know for our equation to make sense. So it says look carefully at the third column showing your pattern. So if you look at the third column where we had that equation, they wanted you to look at what changed. So your input value basically was that 0. So those were the things that were the 0, the 1, the 2, the 3, the 10, etc. That basically changed. And then your rate of change, that was the 70. That basically stayed the same. That stays the same. And then your initial value, that was your 30. That stayed the same. And then your output value was those things that were like the 30, the 100, the 170. Those were your output values. That was your things that traveled, and that basically, that changed. Okay, so it says choose the words to write the general form for a linear equation. So in that order from the table. Okay, so if you look at it, the thing that was on the left of the equal sign, that was your output value. And that equals that next number, if you look, was the 30. That was your initial value. And then plus, so that was, that initial value was the 30. That stayed the same. That never changed. This, the output value, normally we're going to basically call this, and we're going to change this later. I'm going to call this an output variable later on, because you're essentially going to make a letter out of it. You're going to call this a letter later on, but you're always going to put a number in the initial value. Plus, this is going to be your rate of change. That was the thing that was the 70. And then plus your input value. And this input value down here, later on down the road, I'm going to change this to call it an input variable, because for right now, when you write equations, I'm going to change these to letters later on. So these are always going to have numbers in them, whereas these are always later on down the road going to be letters when you write equations. But for right now, in your example, they were numbers, but those are always going to be letters later on down the road when you write equations. So you see how on the next page, oops, I tell you here that your output value and your input value, when you write equations, it's only a value if there's a number here, okay? So think of these as output variables, because you're essentially, when I have you write equations, input variables, because you're going to write letters there. So essentially, you're always going to write letters here and numbers here. So that was kind of basically what they said on the last question. It says sometimes we refer to abbreviate input and output variables with a single letter that makes sense in the problem. As long as the variables are defined, you can choose any letter. For example, one way is to write the equation as a D and a T. So it says write the equation to predict the number of miles after 15 hours. So all they want you to do basically is to plug in 15 and for T. So you would do 30 plus 70 times 15, and that's going to give you 1,080 miles. And it says write your answer using a sentence. So basically after 15 hours, the distance from Austin is 1,080 miles. But in general, this is how you would write a linear equation. You would have variables for your input and your output. And we'll do those in a couple seconds. Okay, so number 3 basically is a population of monkeys that start at 40. So this is your initial value. So that's where you start, and they increase at 5 per year. So this is your initial value, and this is your rate of change. It says answer the following questions and define your input and your output variables. Basically, the one that's in your equation, this is your input variable, and then this number over here is your output variable. So which number represents the number of monkeys? So if they're talking about the population, they're talking about P. Your population of monkeys starts out at 40 and increases by 5 per year. So when they say per year, this is my number of years. So my population of monkeys, they're representing with P, and they're representing the number of years with N. And so my N is my input whereas my P is my output. Just remember that whatever is in the equation is your input, and whatever is on the outside is your output. Okay. An important part of your equation is whether the output values are increasing or decreasing as the input values are, as the input values increase. So if the input values are increasing, then the rate of change is positive. How do you think the equation will change if your input values are decreasing? So if your if your output values are decreasing, then your rate of change, will be negative, and you'll basically see a negative rate of change. It says, write equation for the total amount of money when the initial value is 400 and decreases by $5 per day. So I want the total amount of money in an account. So we'll say A, when the initial value is 400 and the value decreases by $5 per day. So it decreases $5 per day. And so we'll basically say that A is your total amount of money, and D is your number of days. So A is your amount of money, and D means your number of days. Okay, so on 5, it says the equation A equals 1,000 plus 60N, where A is the amount in the account and N equals your number of years, is represented by the table below and the graph below. It says, where is the initial account located in the graph? So your initial amount, or the initial amount in the graph, is located right here. Basically, it's on your y-axis. So it's on where you're on your y-axis, where the x value is 0. And so it's at the point y, or it's at the point 0, 1,000. Okay. And then, is this a linear equation? Yes. So you have a constant rate of change. Constant rate of change, which is the 60, excuse me, which is the number of years, which is $60, which is the amount of dollars in the account, which is basically $60 per year. Looks like the account goes up. That's a constant rate of change. Okay, so let's look at another section 4. The scatter plot shows your miles per gallon and the weight in pounds of the vehicles. The line drawn in the graph is the regression line. The equation of the regression line is given on top of the graph. Regression line is a tool that is used to make predictions about future. So you have a scatter plot in here. And so you notice that all of the dots are not perfectly in a straight line. So what they do is they take all of these points and they basically figure out what's called, they get a regression line. So they basically find all of these, what's called residuals. And that is basically the distance between all of these points. And they try to find a line that fits in the middle of the graph, the equation of a line, which is this equation up here, 45.57 minus 0.0051 V, whatever you want to call that letter. They find a line that fits in the middle of this graph that could best represent a line that would at least predict a pattern. So that if I wanted to say, for example, based on that data, I can use this data to say predict what a vehicle at 2,000 pounds, what its mileage would be, or find another vehicle that was at, say, 4,100 pounds would be right here. I could find that out based on this line. And so your calculator does this, you're not going to have to do this, but that's basically what this regression line basically does. That regression line just goes through the middle of this. So A says we often call the input value the independent variable. Again, this is just reviewing. What is the input variable? Your input variable is your vehicle weight. and that's in pounds. And then what is your dependent variable? So your independent variable is your input. So they just changed wording on this. So your independent variable basically is your input. Your dependent variable is your output. That's your mileage. That's in your miles per gallon. Okay, so it says using the graph, make an estimate of the interval of mileage values for a vehicle weighing 4,000 pounds. So all they want you to do is to make a reasonable estimate for 4,000 miles. So for 4,000 miles, all they want you to do basically is 4,000 is about from here to about here. So I would say that's about maybe like 20 to about 35. So maybe about approximately about maybe about 20 to maybe about, not 35, maybe about 20 to about 34 miles per gallon. So when they say a reasonable interval, that's what they want you to do on that one. So it says use the equation of the regression line. So they're wanting you to use, oops, let me use a different color. So they want you to use the equation, oops, hold on. I want you to use the equation, so they want you to use this to interpret the initial value. So if you have your mileage equals your 45.57 minus your 0.0051 times your vehicle weight, your initial value is this 45.57. Okay, so when they ask you to interpret it, basically that means that for a vehicle, so an initial value, and you don't have it on here because the graph doesn't go all the way, for a vehicle with zero, oops, for a vehicle, I should say, not with, for a vehicle that weighs, because you're looking for interpreting what that means. So it's what that y-intercept means. For a vehicle that weighs 0 pounds, because that's what your x-axis is. For a vehicle that weighs 0 pounds, we expect to get 45.57. But obviously, miles per gallon. But obviously in the real world, do you have any vehicle that really weighs, oops, hold on. But do you really have any vehicle that weighs 0 pounds? So hence, that's why they had the gap. So that's why there was a gap in the graph, because in the real world, you don't have a vehicle that weighs no pounds, but mathematically, that's what it would mean. Mathematically, a vehicle that weighs 0 pounds would give you 45.57 miles per gallon. But realistically, in the real world, that you don't have a vehicle that weighs that. Oops, I guess that's what E means. Sorry, I didn't even read ahead. It says, no, hold on. I didn't even read ahead. It says, no, does this make sense in the context of the problem? No, you don't have a vehicle in the real world. Have a vehicle in the real world that weighs 0 pounds. So vehicle can't weigh 0 pounds. Okay. F says sometimes a model is only valid or useful within a certain range of input values. For what range of input values do you think this model is valid? So if I give you a graph, oops, I didn't mean to do that. I was trying to get an arrow. So what they're talking about is this particular graph gives you a bunch of data points. So all they want you to basically do is tell me what range do these data points go between. So this model here is only valid for things that went between 1,000 pounds and about maybe like 7,000 pounds. So this would not hold, this equation would not hold for a vehicle, say, that weighed 500 pounds or one that weighed 10,000 pounds. So we're going to say one that went from about 1,000 pounds to about 7,000 pounds is what it holds valid for. Explain the trend in the context of the graph. So again, this is where you have to write me a full sentence. So as your vehicle weight increases, my mileage in miles per gallon is going to decrease. So that's the first part. So as the vehicle weight increases, my miles per gallon decreases. Okay, that's the first part of the question. And then it says, does this make sense? Yes. Yes, you would expect heavier cars to use more gas, so the miles per gallon is going to be lower. And then it asks, is this association weak, moderate, or strong? And I would say those ones are spread out a little bit, so I would probably say this is maybe moderate. I would probably say it's moderate. They're not all right on the graph, so I would probably say this is moderate. Okay, this says use the equation of the regression line, which is this. So which is your m equals 45.57 minus your 0.0051 times your vehicle weight to interpret your rate of change, which is this number. And they want you to interpret it. So basically for every 1 pound of vehicle weight, so for every 1 pound of vehicle weight, and this is a negative number here, your miles per gallon decreases, because it's going down, decreases by 0.0051. So you basically just tell me for every one, so anytime I ask you to interpret your rate of change, you just say for every 1x, my y does this. So for every one of my input, what does the output do? That's basically what you have to do for all of these. For every 1x, what does my y do? Okay, this says use the equation of the regression line. So again, it says to use this equation to predict the mileage for a vehicle that weighs 4,000 pounds. So I need to basically plug that into the equation. So my mileage equals 45.57 minus 0.0051 times a 4,000 pound vehicle. That's going to give me 45.57 minus 20.4, which is going to give me 25.17. So my mileage is going to give me 25.17. And then it says, can we be very confident, moderately confident, or not at all confident that the prediction is close to the actual mileage? So if I look on my graph, let me see if it'll let me, I don't know if it's going to let me shrink this or not. Okay, let me add in another image. I'm going to add in another one on here. It might be better. Okay, so for the 4,000 pound, I'm going to try to draw on this picture. So for 4,000 pound, you're about right here. So they basically want you to know is that going to be an accurate representation? Oops, hold on. Is that 25.7 going to be an accurate representation of those ones that are around it right here? Basically, those two that are here. Ooh, that's probably not a good one. Let's do that again. So is that, let's use a highlighter instead. Let me get a highlighter. Let me find a highlighter color. Is that 25.57 going to be an accurate representation of those ones that are right there? Okay. And so if you look at that pink dot in the middle, I want to know, and I kind of did it sideways, it's kind of hard to see. I want to know, is that 25.57 an accurate representation? This is I, of that, since the association is moderate, okay? I still want to say it's not exactly, I would still say it's probably a moderate representation of it. It's still, I'm just going to say that it's, ooh, let's change this back to a pen instead of a marker. So I'm still going to say it's going to be, it's not perfect, but I'm still going to say it's going to be a moderate representation of those points. So since this was a moderate graph, I'm just going to say that's a moderate representation. So compare your answers for C and I. Yes, they agreed. We'll just say that they were moderate for that. Okay, and because if you looked at C, that range was about 20, I don't remember what we said. I think we said it was like 20 to 30 something, like 20 to, I don't remember what it was, 20 to like 33 or 20 to 35 or something like that. And that's about in the middle. So that's about right. Okay. Number 2, it says scatter plot shows the teacher's average pay and expenditures per pupil in a state teacher's public schooling in 2007. As the data are graphed, which is your independent variable? And so that would be the average pay. That's this one down here. And then my dependent variable is the expenditures per pupil. Okay, it says interpret the rate of change in the regression line. So if you look up at the equation up above, my rate of change for that, hold on, okay, is this number right here. So I'm going to round that to about 23 cents because that's 0.2281. Okay, so this is my rate of change. So basically, the expenditure, so for every $1, for every $1 increase in average pay, teachers spend 23 cents expenditure. I can't spell. Expenditure per pupil. Per, I should say 23 cents more per pupil. Per pupil. Per pupil. Okay, explain the trend in the context of this graph. Is it a strong, weak, strong, moderate, or weak? So basically so you can kind of see my graph is going up. So you don't say as your graph is going up, you use a complete sentence. So, oops. So as the average pay increases, expenditure per pupil increases. So you have to use, I need to see what the X does, what the Y does, and I need to see the increases and the increases. From the scatter plot, oh, and is it strong, moderate, or weak? So on this one, this is still spread out some. I would probably still say this is moderate. It's probably getting to a weak side, but it's still probably moderate for my graph. From the scatter plot, estimate a reasonable expenditure for pupils for a teacher average of 55,000. So for 55,000, it looks like she spends from here to here. So that's about here to here. So I'm going to say that's about, so 55,000. So I'm going to say that's about like maybe like 8,900 maybe to about 55,000 to about 12,000 maybe, approximately. It's kind of hard to see from the graph, so approximately about that much. Okay, so this one actually says to use the regression line, oops, to calculate the expenditure for 55,000. So I'm actually going to use the equation. So my expenditure is going to be negative 1325 plus 0.2281 times 55,000. So when I do that, I get negative 1325 plus 12,545. It's going to give me about 11,220.50. And so it says, can we be very confident, moderately confident, or not confident at all that this prediction is close to the average expenditure? So it said the association is moderate, so I would just say we're still going to be about moderately confident. So it's still in about the range. So that's what they're going to spend. So we're still about moderately confident just because this is moderate. So we're not exact, but we're still in the ballpark. Okay, so is the height of a woman's brother or mother more helpful in predicting the height of a woman? The graph shows the data for 42 adult brother and sister pairs, the same 42 women paired with their mother. The 43rd woman not included on the graph has a brother who is 68.5 inches tall and a mother who is 62.5 inches tall. Use the regression equation to predict the woman's height from each model. So if I do my equation, so that's 11.47 plus 0.8156 times 68.5. That's the brother's height. That's going to give me 67.34. And then if I do the 50, and it says, and a mother who is 62.5 inches tall. And then if I do 5.714 plus 0.9126, times 62.5, that gives me 62.75 inches tall. That looks a little messy. And that I'm getting from these equations that are over here. And so it says, which prediction is likely to be closest to the actual value? So if you look at the two graphs, okay, here's the woman's height with the brother's height, and here's the woman's height with the mother's height. And since there's a stronger association between the woman's height and the mother's height, because you'll notice that these dots are tighter, we can expect that this 62.75 is going to be closer to the actual height. So since the mother has a stronger association than the brother, you can expect it to be more accurate. You can expect it to be more accurate. So this one here is better than the brother.